All right, so here's our first problem for our practicum session tonight. We have a box on a wire, and that box we have supported, we got a 1,000-pound box, and it's supported on this wire so that the right side wire, part of the wire is horizontal and anchored to a wall over here. And then we've got this slanted piece that is off up and to the right, up and to the left, and it's set up so that it's angled 30 degrees to horizontal. So the goal here is to find T1 and T2, and we want to find those to 3 significant figures. So we want to make sure that we've got our answers good to 3 sig figs. So I'll stand by here for a few minutes to give you some time to try to set that up on your own and see if you can figure out what the answers are, and then I'll work through the problem. All right, so first thing to ask yourself when you're looking at this problem is, do I believe this is in equilibrium? Is it physically reasonable? And it looks to be physically reasonable. It looks like you'll have a tug of war, no one's winning. You've got forces pulling down here, and you've got down and up and to the left to oppose that, and you've got to the right. So there's a mix of forces here and a mix of and a structure here that looks like it should be able to work, as long as the rope is strong enough, or the chain or the wire is strong enough to handle it. So the first thing we need to do is draw a free body diagram and define our coordinate system. And in this case, since we're trying to get at the tensions in the wire, the best point to choose would be that point at the center right there, where all 3 of those forces connect together. So we'll go off to the side down here and draw our point where those 3 connect. One of the fundamental ideas in dealing with systems in equilibrium is that if the system's in equilibrium, then every little piece of that system's got to be in equilibrium too. So if this overall structure is in equilibrium, then that point has got to be in equilibrium too. And that point's the easiest one to analyze. Now, since wires can only be in tension, be pulling, we'll draw T1 or T2, excuse me, off to the right here. We'll draw T1 up and to the left, and we'll translate in that 30-degree angle. And then we've got a force pulling down, and since that wire is only connected to this box, it's reasonable to assume that if this box weighs 1,000 pounds, then there must be 1,000 pounds of force pulling on that rope or on that wire. So this is 1,000 pounds of force straight down, and we'll define our coordinate system. We'll use the traditional one. To the right will be positive x, and up will be positive y. So there's our free body diagram and our coordinate system. The next step is to sum the vectors, to add the vectors up. And to add the vectors, we break them up into components. We break them up into components. We add all the x components together. We add all the y components together. That's the basic setup for adding vectors. So I'll go through and call that vector 1. We'll call T2 vector 2, and we'll call the weight vector 3. So vector 1, that's kind of the hard one, so we'll skip that for the moment. We'll go over to vectors 2 and 3, which are a little easier to describe. So vector 2 has all x component, and it is just T2, whatever the tension is in that rope or in that wire. It has no y component, so we can put 0 there. Vector 3 pulls down, so it's all y component and no x. And this says a little bit about our coordinate system. The coordinate system is usually a choice. It's usually a choice we get to make. We can pick that coordinate system to be pointed in any direction we want. You generally want to set it up so that it simplifies the most number of vectors. simplifies your unknowns if you can, because simplifying the unknown is working with a simple unknown is easier than working with a more complex unknown. If I angled this, made down and to the right positive x, then I'd have sines and cosines involved here, and that would be more complex. So setting it up, when you pick a coordinate system, you should always pick it to make things as simple as possible for you. But here I can't avoid having some components where I'm going to have to deal with sine and cosine. I've got T1. Now this is different than the problem we did at the end of lecture, where we had nothing about the vector, where we didn't know its size or its direction. In this case, we have the direction. And this is a problem we can solve because we do have two unknowns. The most we can ever handle in these kinds of problems are two unknowns. In this case, the two unknowns are both magnitudes. We have a direction. So it wouldn't make a lot of sense to do T1x and T1y here. Instead, we're going to use T1, but we're going to use sine and cosine, because the sine and cosine are just going to be numbers, sine and cosine of 30. So our horizontal component is going to be, since it goes with the adjacent side goes with cosine, this will be T1 cosine of 30 degrees. And the vertical piece, since it's the opposite side, will be T1 sine of 30. And I'll write that down over here a little more clearly. X is my horizontal, so that'll be T1 cosine of 30 degrees. And Y will be T1 sine of 30 degrees. Now, unfortunately, cosine and sine of 30 degrees, not the nicest numbers. They're better than some, but we can go and actually calculate those out. If we knew what T1 was, we just multiply it by cosine of 30. Cosine of 30 is 0.86603, and we get a number. But since we don't have the value for T1, we can still get the cosine of 30. We can get that number and write this as 0.86603 T1. And here I'm keeping 5 sig figs because in the problem statement it told me to keep 3. By keeping 2 more sig figs than what I need in the end, I'm going to keep all my round off error down in those 2. And when I finally round in the end to the 3 sig figs, I'll round off all my round off error and have a good accurate result. Now with sine of 30, I don't have to do any rounding because sine of 30 is just 0.5. So I'll have 0.5 T1. So the coefficients of our unknown T1 are the sine and cosine of 30. So there we've got all of our vectors broken up into components, into x and y, so we can do our sums. So that's our next step. After we've broken up the vectors into components, we take our sums. So we'll take our sum of forces in the x direction and our sum of forces in the y direction. Well, in the x direction, we've got T1 cosine 30, which was 0.86603, times whatever the magnitude of T1 is. But that pulls to the left. And by our coordinate system, to the right is positive, so to the left must be negative. So that's got to go into the sum negative. Then we've got T2, all x component and all to the right, so that goes in positive. And then we get nothing from the x component for vector 3. Then we have our sum of forces in the y direction. In the y direction, we've got 0.5 T1. And that's up, so it goes into the sum positive. Y up is positive. Vector 2 has no y component, but vector 3 does have a y component, and it's 1,000.
Negative.
Negative, because it's down.
Yep.
So it's down, so it's negative. So there are our sums. If we had values for T1 and T2, we'd get numbers and we could work with those. But here we've just got these sums in these unknowns, T1 and T2. But we have one more piece of information. This is an equilibrium, which means that the sum of forces in the x and the y directions both have to equal 0. So while we might not know what the values are over here, we know what they add up to. It's got to add up to 0. So those are our equations of equilibrium. These two right here are the equations of equilibrium. And we should be able to solve those because they only involve two unknowns. Now we're in the problems we did in lecture, we had pretty easy equations to solve. This one's a little bit a step up in difficulty. It's not as bad as it possibly could be, but it's a little bit harder. If we look at the x direction equation, we actually can't solve that right now. We don't have enough information to solve it. It's one equation, but in two unknowns, T1 and T2. But the y direction equation we can solve. The y direction equation only has one unknown. So if we go over here and solve the y direction equation, we've got 0.5 T1 minus 1000 equals 0. If we add 1000 to both sides, we have 0.5 T1 equals 1000. Then we'd have to take that final step of dividing by the coefficient, in this case 0.5, and we get our value T1 is 2000. And that is a force, so we'll label it in pounds. So T1 is 2,000 pounds. Even though we're only hanging a weight here of 1,000 pounds, because of the angle involved here on T1's got to pull a lot harder because only its vertical piece is going to support the load. So there's 2,000 pounds of tension in T1. So we've got half the problem done. We have the tension in T1. We now need T2. Well, now that we've got a value for T1, we can solve our x direction equation. We can plug in this value into the equation and we'll just have an equation left for T2. So let's go ahead and do that. We have negative 0.86603 times the value of T1, and the value of T1 was 2000, plus T2 equals 0. And if I go over to the calculator, 0.86603 times 2000, I get 1732.1 rounded to 5 sig figs. So I get 1732.1 negative plus T2 equals 0. Now to solve that, I just have to get rid of this negative 1732.1. So I'd add that to both sides. And that would give me T2 equals 1732.1 pounds. So we got our values T1 and T2. We're not quite done yet because we have to satisfy the objective of the problem, which was to write the answers to 3 sig figs. But we've got our good to 5 sig figs answers. In fact, T1 is exact. T2 has some round off in it because we rounded here and we rounded again here. So there's definitely some round off error on that one. But we'll fix that when we round to 3 sig figs. But there we have our values for T1 and T2. So let's go ahead and round those off. Let's take care of T2 first. So I'll go up here to present my final answers. T2 I had 1732.1. Rounding that to 3 sig figs, I'd have to round in between the 3 and the 2. So that would be 1730 pounds. Remember that trailing zeros don't count unless there's a decimal point involved. T1's a bit of a challenge. I can't really round T1 to 3 sig figs. There's not a way to write that. The way it's written, it looks like 1 sig fig. If I put a decimal point at the end, it looks like 4. So I'm in one of those weird situations where I really can't write the number out with 3 sig figs unless I write it in scientific notation. So scientific notation always saves us in those situations. So if the problem had the specification on it to write your answer to 3 sig figs, and you had a number you couldn't really write to 3 sig figs in the full format, go ahead and write it in scientific notation. I'd write this as 2.00 times 10 to the third, and don't forget the units, pounds. Now that's definitely 3 sig figs because trailing zeros after the decimal point count. So that's a little quirk. That would not be worth a whole hell of a lot in a graded situation. It's really more about just meeting the objectives of the problem. As far as calculation goes, 2,000 pounds is a fine answer. But one of those things in engineering, you always have to meet your specifications. So there's our final answer, T1 and T2.
All right.
Make sense there?
Yep.
All right. I think that's probably a good place to pause and let this sink in a little bit before our next session. So next time we'll do a couple more practice problems. I'll introduce a couple more complexities into things where it's not so clear what direction to draw things in. Because sometimes when you've got multiple forces, you may not know what direction. You may be taking a guess as to what direction you're drawing things in, and that means we have to have some way of figuring out whether our guess is right. In all the problems we did tonight, we had no question as to what direction our unknown forces needed to be in. When there are questions about it, it can be a little bit more challenging. So we'll work on that on Wednesday.
All right. Sounds good.
All right. Have a good night.
Yep. You too.
Thank you.